Hello everybody and welcome to Make 102, Introduction to CO2 Laser Cutting. A few items about this training. There are quiz questions embedded within the video and you will not be able to skip forward in the video. Every time you answer a question, you will eventually be presented with the option to retake that question. This is important because you must score 100% on this training to be able to use the laser cutters after taking it. So please make sure you review questions that you get wrong and retake them until you understand the answer and get it correct. Okay, so let's jump right in. In this training, we are going to cover what you can do and make with laser cutters. We're also going to look at the principles of lasers and what is a laser and how we characterize lasers. We'll look at the design of laser cutters and how they operate and the theory behind that. And then we'll go into preparing design files for the laser cutter and how to operate the actual machine. All right, let's get started. So the first topic we are going to discuss is what you can make and do with CO2 laser cutters. So there are two primary things you can do with a laser cutter. One is you can cut, and two is you can engrave. So if you look at this item here in the center of the screen, this was created from a larger piece of wood. So we have a cut line going around the entire part here. So one thing we can do with a laser cutter is cut completely through the material. Another thing we can do is we can engrave the material. So you can see in the area around the text here that we are removing material, but we're not cutting all the way through the part. That's the same for these other lines all the way around the part. So we can do two things. We can cut and we can engrave. So we can make functional prototypes using CO2 laser cutters. These are items like you see in the front of us. These are toys or demonstration objects where the entire product is made from laser cut parts. We can also make parts and systems that combine one or two modalities of making. So if you look here, we have items that have 3D printed parts on them, screws and bolts, plastic laser cut parts like here, and electronics. So we can combine all these things to make functional prototypes. We can also create things like joints and bendable hinges made from wood or acrylic. And we can create end-use products that have a certain look and feel from them being made in a particular material. The concept here is that laser cutting is a very versatile prototyping and production process. You can make many, many different things from it. For example, here we have acrylic combined with wood, combined with fasteners and components. These are very versatile technologies and they can be used for a variety of things. For example, as well, consider the prototype on the right here. This is a 3D printer that is made primarily from laser cut wood parts. Now, we might never do this for a production product or even a final product, but we might decide to laser cut all of our components that can be laser cut initially out of a cheap material like wood to test everything before we build it out of a more permanent or more expensive material. This is a very good step in prototyping to do things quickly and cheaply to make sure that everything is going the way we want it to. Next, we're going to move on to laser principles and characterization, and this is how we think about lasers and what they are. So since we are going to use a laser to do some work for us, we should understand what a laser is. So we are all familiar with sunlight, which is the light coming to Earth from the sun. And this light is scattered light that is in multiple frequencies and non-coherent. So what that means is it contains waves of photons at different wavelengths. That's what gives these different waves different colors. So the light coming to us from the sun actually has multiple colors of light in it across a wide spectrum of frequencies. And it's also non-coherent. So these waves do not run parallel to each other, and they also are out of phase with each other. So this is sunlight. Now, let's consider something we may be familiar with, LED light. This is what comes from light-emitting diodes. Typically, this light has a single frequency in it. It may be a little better than that, but usually it's a single frequency and it's also non-coherent. So that means all the waves coming out of the LED are of the same frequency, but they are out of phase with each other and not necessarily in the same plane. So that's sometimes why light that comes from LEDs makes things look harsh. Now with laser light, there is only one frequency, and all the waves are coherent. So all the waves line up with each other, they're all in the same plane, and they all are at the same frequency. So this means laser light is very coherent. And if you remember from your study of physics, when you have two waves that are coherent and they overlap, the resulting wave ends up with a higher amplitude. So this is one of the reasons that lasers are very damaging to the human eye, is that when all of these waves overlap, they create a wave that has a very high amplitude. So now let's look at how we characterize a laser. So if we have a laser source, and that source is producing a beam of laser energy, that beam will have a particular wavelength. We could also denote that with frequency. It'll have a particular diameter. How big is the diameter of the beam coming out of the laser? It'll have a particular amplitude, and the amplitude also indicates the power of the laser. So sometimes when we refer to lasers, we'll refer to them by the wavelength or the frequency that they produce, but sometimes they will also be referred to as the type of gas that is used to produce the laser. And that is because these two things are related. If you have a CO2 laser, you will get a wavelength of between 9,300 and 10,600 nanometers. So sometimes you will see a laser referred to by its gas, like a CO2 laser. Sometimes we also refer to the beam diameter as spot size, and sometimes the amplitude would be listed in watts because those two are directly related. One thing that is pretty typical of industrial lasers is that most of the time they do not stay on 100% of the time. Some lasers are not even capable of staying on 100% of the time. So they pulse. We turn the laser on and we turn the laser off very quickly, which for certain kinds of applications doesn't affect the way that the application or laser cuts, although sometimes it does. So we sometimes will see a frequency and duty cycle of pulsing for the laser. So now that we understand some basics about how lasers operate and how their specifications are derived, we have to talk about laser safety. Now there are two types of laser safety. One is for open lasers. This is the kind of laser you might find on an optical table in a research lab or something of that nature, where the users around the laser could be directly exposed to the laser beam. And the other kind is contained laser safety, where the laser radiation is contained within an envelope or a machine. We are dealing with the second kind. All of our lasers are contained within the machine. So we classify this in class 1 through class 4. And class 1 machines, the laser radiation, the accessible laser radiation, is completely harmless. That means the amount that gets out of the machine is a harmless level. Class 2 is essentially the same as class 1, but it contains visible light lasers. So all of our lasers in our space are class 2 lasers because they have a visible laser pointer on them as well. The laser radiation that does the actual cutting is invisible, but the pointing laser is visible. So we are class 2 lasers. Class 3 is where the accessible laser radiation can be dangerous, but our systems will shut off if you open the enclosure. So they are not class 3 lasers. Now, some of our lasers have a door that can be opened that would turn them into class 4 lasers. If this is the case, the users would need to wear additional protective equipment. And right now we do not support this in the makerspace, but if you need to do this kind of cutting, you can ask the staff and maybe it can be arranged. So because all of our lasers are class 2 lasers and they do not allow an excessive amount of laser radiation to escape, what that means is that you can operate these lasers with no additional protective equipment. All right, so let's start talking now about how laser cutters actually work and how they cut material. So at the top of the laser cutter, we have a laser source. This is emitting laser radiation down. At the bottom, we have some material, and the laser beam puts that energy onto the material, and that is going to cause the material to heat up. So a few things to notice. There is some reflection, some amount of laser energy is reflected. This is something that we do not want. And also that the zone that gets heated is wider than the laser beam. So the way this works is the material heats up and the material either disintegrates, vaporizes, or melts away. So we are essentially obliterating the material here by melting it in most cases. So what determines how much of this laser energy is reflected? We stated before that we don't want the laser energy to be reflected. Essentially, this is a characteristic of the material. It's a function of the material properties. Now, it could have to do with the reflectivity of the surface of the material. So shiny materials may cut less well than dull materials. But in essence, the major factor is the wavelength of the laser combined with the material. So what that means is, for example, look, we have two lasers of equal power here. One is a CO2 laser, which means it has a given wavelength, and one is a fiber laser, which means it has a given wavelength. And in this case, it's the wavelength of the laser source that determines the reflected energy. So if we tried to cut steel with a CO2 laser, we would have a high amount of reflected energy. If we tried to cut steel with a fiber laser, we'd have a low amount of reflected energy. And this means that certain kinds of lasers are much more suitable for cutting certain types of materials versus other materials. Before we continue on, please take a look at this list of materials that are usable on the laser cutters that we have here in the Makerspace. The list is divided into two categories: cutting and engraving, and this lists the materials that you are allowed to cut in the Makerspace. Next, please consider that there are materials which cannot be cut on a laser cutter and are not allowed to be cut. The most common is PVC. PVC is very hazardous to cut in a laser cutter. These warnings come directly from the laser manufacturer, so please do not cut these materials on the laser cutters in the Makerspace. Also, specifically, no metals can be cut on the laser cutters in the Makerspace. Our CO2 laser cutters are not capable of cutting metal. We do have a fiber laser cutter that can cut metal, and if you need to do that, please contact the staff. So now that we know a particular kind of laser can only cut a particular set of materials, once the laser is cutting, what happens to that material? And we already discussed that it disintegrates, vaporizes, or melts away. But if it vaporizes, where does it go? And it goes into the atmosphere around the cut. And if you can smell something, what you're smelling is tiny particles of that material. And in many cases, we do not want to inhale the vaporized material from laser cutting. So we need that material to be exhausted away somewhere safe. So our systems have an exhaust system that will pull that material away. So we want to make sure if we are smelling the cut, something may be wrong. We should not be smelling the cut when we are cutting with the laser. And we should also verify that we don't cut particularly hazardous materials, because no exhaust system is perfect, and we don't want to be inhaling hazardous material. So we have been using this simplified diagram of a laser cutting system so far. But the truth of the matter is most industrial cutting systems do not have enough power to operate as shown. The energy concentration in the area below the laser beam simply is not enough to cut material. So to do this effectively, we would need a very high laser power, or we need to increase the energy concentration. And this is the way most laser cutting systems work. We find a way to focus the beam to a smaller point. So how do we increase the laser cutter energy concentration? We use a lens. So this is where we place our lens. We place it in the beam, and it starts to taper the concentration down to a single point. The point where all the energy is focused, we call the focal point. This is where the highest energy concentration is. the distance from the lens to the focal point we call the focal length. Now, for a cut to succeed, we need the entirety of the material, the whole height of the material, to be within the focused zone. So this zone here has smaller diameter than the initial beam. A few things to note: that once the beam goes through the material, there is still laser energy below the part. So this can be a problem because there can be things below the part, like the support material holding the part, small pieces from previous cuts. So we have to be mindful of what is below our part. Another thing to notice is that if the energy concentration is too low, it will not cut the material. Even if you make repeated cutting passes, it still will not cut. So this is the problem that can happen if we try to cut really thick material. So to recap that, these lines represent the initial diameter of the beam. So we have determined that the beam being this diameter is not focused enough to cut the material. So any energy that is wider than the initial beam diameter does not have enough energy to cut the material. So for a successful cut, we need the entirety of the material to be within the focused area. So what you're seeing here would likely yield a successful cut. The focused area is completely within the material. So let's consider that we now want to cut a thicker piece of material. To do that, the solution would be to use a lens that has a longer focal distance. We'd want to make this focal length longer. But if we were using the same lens and same setup that we were using for the thinner material, we would have a problem. The laser would succeed at cutting this deep into the material, but everything below that deep would have too low energy concentration to go all the way through. The beam spreads out wider than the diameter than it even was initially. So we're not going to have enough energy concentration to cut through the material. Even if we ran the laser over the same material multiple times, if the material is too thick, it simply will not cut through. So if we wanted to successfully cut thicker material, what we would need is a laser with a longer focal length lens. This would decrease the beam angle, leading to a larger distance that can successfully be in the focal zone. This will also mean the distance from the lens to the top of the material is also longer. So if we have thinner material, we want a shorter lens. If we have thicker material, we want a longer lens. Now, we have several laser cutters. Our Speedy 100 laser cutters have a fixed lens of 1.5 inches. So you cannot change the lens on these machines. If you have to cut thicker material, our Speedy 400 lasers have interchangeable lenses. So if you need to cut material over about a half an inch thick, you should be on a machine with interchangeable lenses, and you should ask the staff to help install a longer focal length lens. So when we are laser cutting, the center of the beam is what will follow the cut lines that we tell the laser to cut on. As we know, the laser will cut a certain width through the part. It will not be an infinitely small cut. We refer to this width as kerf, or kerf width. This is the width of the cut that the laser makes through the material. Now, this will vary from material to material, and it can vary from laser to laser, and it certainly will vary from lens to lens. So if you are cutting something that has particularly tight tolerances, you may need to measure the kerf width before you cut your final part to come up with the actual dimensions that you want to cut. So here is an example of how kerf width affects the cut that you make. The gray box here represents the raw material, and this is the target part that we want to cut. It's simply a square of a particular dimension with a hole cut in the middle of a particular dimension. So when we cut, the laser is going to follow the line that we told it to cut on. So That is represented here by this red line. So the laser is going to follow that line, but it's going to remove material on both sides of that line. So if the laser follows this outside perimeter all the way around, if it does that, it's going to be following this line, but it's going to be removing material here and removing material here. So that means that the actual part is going to end up being smaller than the part that we wanted. Now, usually the kerf is only a couple thousandths of an inch, but for example, if you need two parts to press together tightly, this will make a big difference. So if we're cutting the outside of a part, we would expect that the resulting part will be slightly smaller than we expect. If we're cutting inside a feature, like let's say we're cutting this hole, the laser is going to follow the red line, but it's going to remove material outside the line and inside the line, which means the resulting hole is going to be slightly larger than we wanted. So this matters for engineering parts that have tight tolerances. Okay, so let's put everything we've learned together to look at how the laser is actually set up on the machines that we will use. So there is a laser source in the rear of our machine. It produces a laser beam that travels out. It hits a mirror, bounces off, hits another mirror, travels down and hits the mirror in the laser head. The beam then travels down through a lens and travels down through our workpiece and then out the bottom of our workpiece onto the bottom of the machine. A few things to note: our material is sitting on a surface, and each of these little dots here represents a support on the surface of that table. And when the laser beam hits one of those supports, some of that energy will be reflected back up, and you may see that as a small flash. That's normal. Also, there is pressurized air that flows through the laser head. This serves two purposes. One is to potentially extinguish any small fires that occur on the workpiece, and two, to prevent vaporized material from condensing on the lens. So we don't want to operate typically without the air on. These lasers do have the ability to turn the air off in settings if you want to, but most of the time that is not advisable. This head moves around, so the head moves in the positive X direction and the negative X direction, which is that way. So this whole unit can move back and forth. Then this lens here, this moves in the positive Y direction and the negative Y direction. So this whole unit can move this way and that way. And this is what gets the laser from where it's mounted to the Y axis. All right, welcome back from the quiz. Glad everyone is still with us. Now we're going to begin talking about laser cutter operation and workflow. So there are 6 steps in making something on the laser cutter. The first step is to get your design files. You can download these files from websites, or you can create them in a vector design software. Then we're going to prep those files for laser cutting. This means we modify the files to indicate which lines are to be cut and which lines are to be engraved. Then we specify the cutting parameters. So for example, how much power should we use on the cut lines, how much speed we should use on those lines, and what to do with the engraving lines, etc. Then we verify that our setup is correct. We set the machine up, we load the material in, and we focus the machine. Then we cut the job and wait for it to finish, and then we clean up. So now we are going to look at each of these steps in depth so we can learn how to perform each one of them. So step 1 is to get your design files. So laser cutters work on 2-dimensional design files, often called 2D vector files. These are flat drawings, and there's many ways to make them or acquire them. So you can build them in packages like SolidWorks or Fusion 360, or you can use graphic design packages like CorelDRAW and Adobe Illustrator, or you can download these files from existing websites for existing designs. So some common file formats for these designs are .dxf, .ai, .pdf, and .svg. So now that we have our design files, we now need to modify those design files to instruct the laser what to do with each of the lines in the file. So for example, if there are certain lines we want to cut, then we need the laser to treat those lines in a certain way. If there are certain lines we want to engrave or text that we want to engrave, the laser needs to treat those lines differently. The way we do that is with color. By default, the laser treats red lines as cut lines, and these lines have to have the absolute minimum thickness. So if you have thick lines, the laser will not treat them as cut lines. So they have to be red lines with minimum thickness, and there are specific values that you use for that. And for engraved lines, the laser will treat black lines as engraved lines. Now these are the defaults. There are ways to do more than just cut and engrave, like we can score and we can cut to different depths, but that is an advanced feature that you can learn later once you've mastered the basics. So before we move forward, because color is how we will control what the laser does with each line, we first need to understand how color is represented in our files. Color is represented using an RGB color value. This is a red, green, blue value. So each color is represented with 3 numbers. The first number is the red value, the second number is the green value, and the third number is the blue value. Each of these numbers can range from 0 to 255. So a 0 would mean there is none of the color, and 255 would mean there is 100% of the color. So let's take a look at this example right here. We have the set 255, 128, 0. That means 255 is 100% of red, 128 is 50% of green, and 0 is 0% of blue. So this gives us the color orange. If we have 0, 0, 0, that's 0% red, 0% green, 0% blue, so that is black. If we have 0, 0, 255, 0% red, 0% green, 100% blue, so that is the color blue. If we have 0, 255, 0, that is 0% red, 100% green, 0% blue, so we have the color green. And now if we have 255, 0, 0, that is 100% red, 0% green, 0% blue. Now a note on this, this is the color red that we need when we are indicating to the laser that a line is red. If I put a little bit of green in here or a little bit of blue, it will still look red to your eye, but the laser will not interpret that as red. The only red that works is full red, 0 green, 0 blue. Okay, so now that we know how colors are represented and we know what we need to do, we need to make our cut lines as thin as possible, and we need to make them red for cutting, and anything we want engraved, we need to make black. So we create our design files in either a CAD software or we download them from the internet. Then we export them into either a DXF or a PDF file or some other vector file. Then we open those files in one of these 2 software packages, either CorelDRAW or Adobe Illustrator. And when we're in these packages, that is where we change the lines to be what we want. So we change all the cut lines to minimum thickness, and we change them to pure red, and we change all the things we want engraved to pure black. Then, once we have done that, we come out of the software and we go into the print window. And in the print window, we set the cut parameters, and then we send the file to the machine to be cut. So what we're going to do now is look at how to open these files in both CorelDRAW and Adobe Illustrator, and how to set them up to make cuts. So what are CorelDRAW and Adobe Illustrator? These are both graphic design packages that specialize in using vector-based graphics. For our purposes, these are the two softwares that we can use to change the line thicknesses and colors so that the laser will interpret them correctly. So let's first take a look at how we would prepare our files in CorelDRAW. First, we would start CorelDRAW and open up the files. And then we would want to look at a few things around the window. So we want to make sure that our work size is correct for the laser that we are working for. So if you're on the Speedy 100, you want the work size to be 24 by 12. And if you're on the Speedy 400, you want it to be 39 by 24. We want to make sure we're working in the correct units, and we want to pay attention to some of the tools on the toolbar. So as an example, we're going to look at how we would cut out the files for this box. So here are all the pieces that need to be cut out to make that box. And by looking at it at the current time, we can see that all the pieces have black lines. So right now the laser would not treat them as cut lines. So we need to change that and make sure the thickness of these lines is correct, so also that the laser would treat it as a cut line. Then we need to make sure the text is pure black so that it gets engraved. So from whatever package we're in, we export this file as a PDF or a DXF file, and then we open the file in CorelDRAW. So once you have CorelDRAW open, you'll choose File, Open File, and Import, and then select your CAD file. Hopefully it is a PDF or a DXF already, and then you'll click OK. Typically, you want this set to curves if it prompts you. However, if the computer has the same font is installed for the text you're using, everything should be okay. Then what we want to do is verify that the file has been brought into this software with the correct dimensions. So it would be best if we knew the size of our parts. So for example, if we knew the length from this point to this point on our box, we could then highlight that in the software and make sure the dimensions are what we expect. If they aren't, we may need to modify that. Then the next thing we do is we select all the lines that are to be cut lines, and we go under the Object Properties box, which if it's not visible, you're going to press Alt-Enter to bring it up. And then you're going to make sure all the lines have the weight of hairline and that their color is pure red. So 255, 0, 0. Then we select all the lines that we want to engrave. And under Object Properties, we make sure they have some weight, that they are not hairline. They should not be hairline. They can be any thickness. They should be as thick as we want them to be. And we make sure that their color is precisely 0, 0, 0. Now we'll learn to do the same thing in Adobe Illustrator. So when we open up Illustrator, we want to make sure that the size of our work area is the size of the laser we're going to be working on. We want to make sure we are in inches. Then we want to import our file. And then we do the same thing. We first verify our dimensions. So select some line that is of a known length. Check the length of that line to make sure it is the length you expect it to be. Then we select all the lines that we want to cut. And under Properties, we set their thickness to 0.001 millimeter or 0.01 point. We set their color to be exactly 255, 0, 0. Then we select all the lines that we want to engrave. We set them to some thickness that is not the minimum thickness, whatever thickness we want them to be engraved at. And we set their color to be 0, 0, 0, full black. Okay, so now that we have set up our files, we have specified the cut lines and the engraving lines, we now need to specify the cutting parameters. The laser cutter will show up as a printer, and we will configure the cut parameters in the printer dialog. So once we are done with our file prep, we click Print. If we are in CorelDRAW, we are going to see a window that looks just like this after we click Print, and we are going to click Preferences. If we are in Adobe Illustrator, we are going to see a window that looks like this. On the bottom, we are going to click Setup, and then we are going to click Preferences. Once we get to the Preferences and Setting window, there are a few things to take a look at. We want to make sure these checkboxes are in this state, so we want to have Take from Application checked and Minimize to Job Size checked. And unless we are engraving on something cylindrical like a glass, we want Rotary Attachment unchecked. Then next we look in the Materials Settings area here. There are two drop-down menus. The first is the major group, like plastics or woods. And once you select one of those, there'll be a subgroup, which is the particular kind of material. Once you select the material that is closest to what you are cutting, you can observe that on the right-hand side, it shows the settings for each of those materials. So black here, this is the engraving settings. So for this example, in plastic, it would be engraved with 100% power at 50% speed and a laser pulse rate of 1000 Hertz. And then for cutting, in this particular material, it would cut with 100% power at 1% speed with a laser pulse rate of 2000 Hertz. Once you have set these up the way that you want them for the material that you are using, you can inspect the parameters down here. These should normally be the way you see them now. Then you click this Job Control button. This takes the parameters that you have set up and it sends them to the Job Control application, which is what we will use to launch the cut. After you click the Job Control button, you can close this window and then click the Print button on the Print dialog. After that happens, the computer will automatically open up the Job Control application, which we will talk about next. So once we have printed the file, the computer is going to automatically open a program called Job Control. If it doesn't automatically open, you can click into it. This is the software that we use to configure the laser, to arrange where the job is on the laser bed, and to start and stop the laser. So once Job Control opens, you'll be presented with a window that looks like this. There are a few things to consider. First, on the bottom right are the controls for the laser and exhaust. This first button connects the software over USB to the laser. So one of the first things you'll want to do is press that button and wait for the laser to connect. You should also make sure that the laser has been turned on, which we will go on in a future slide. Next, the window over here shows all the jobs that have been printed to Job Control. Your job will likely be at the top. I would avoid having your job named like this, Untitled 1, Untitled 2, by saving your job before you print it with a meaningful name. Up top, this is where all the laser parameters for the selected job will show up. So to start, you're going to drag a file from the right-hand side onto the work area in the middle. This represents the cutting bed of the laser. So your file will show up here, and if you click on that, the parameters for that file will show up here. These should match what you selected in the print dialog. This is also where you can do little tweaks if the job isn't cutting quite correctly. If you do make a tweak, for example, by increasing the laser power or slowing the speed down, make sure you click Save here to update the file. On the left-hand side, this will show you an estimate of the processing time, black being for engraving and red being for cutting. On this page are shown things we just talked about, just enlarged so you can see them a little bit better. Here are the icons that represent the connection state of the laser, the job queue, and down here is the configuration ribbon. So this should be your major category, your minor category, your workpiece thickness, the engraving power, engraving speed, and engraving pulse frequency, the cutting power, cutting speed, and cutting pulse frequency. Now let's take a look at the physical setup of the laser cutter. This is for the Speedy 100 lasers that we have, but it is very similar for the other laser cutters. There is a power switch. On the Speedy 100, it is located behind this little ridge. On some of our other laser cutters, it is the key. Next to that is the emergency stop. You can always feel safe to press this if something goes wrong, although please note it will not put out a fire if there happens to be a fire in the laser. Below are the movement controls, and this is the main process chamber door. Of note, if you open this door while the laser is running, it will shut down, and you may not be able to recover from that. So only open the door if there is something wrong going on if you are already cutting. Inside the process chamber, there are a few things to pay attention to. This is the main cutting head assembly that we have been looking at. There is the mirror. The lens is in here. And this is the air nozzle. This differs from laser to laser. Please do not touch the lens in there. If you need to touch this or move around within the laser, please try to avoid touching the lens. This whole unit here is the XY gantry that moves, so be mindful of that. And this grate on the back of the laser is where the exhaust gets pulled from. On the front control panel of the laser, there are a few buttons to pay attention to. This turns the exhaust on and off. This should happen automatically when you start cutting, but for example, if you need to clear more fumes from the build chamber, you can press this and it will turn the exhaust on. This is the standby button. This leaves the laser on but turns all the critical components, including the laser, off. So if the laser is making a lot of noise, you can press this and it will stop making noise, for example, while you're working or in between cuts, and this button will pause your job. Down here are the movement controls. These two controls move the laser in X, and these two controls move the laser in Y, and these two controls move the work bed up and down in Z. We have a custom designed exhaust controller, which I happen to have designed and built. If you have any questions about it, feel free to ask me. This is the combination of an exhaust fan located on the roof of the makerspace with piping that goes down to each unit, and then in front of each unit is a blast gate. This blast gate can open and close, allowing airflow to each unit. In the picture, if this box is green, that means the exhaust fan is running. And if this box here is green, that means the blast gate for that particular laser should be open. So this is laser cutter 1, laser cutter 2, laser cutter 3, and laser cutter 4. It is your job to make sure that this system is always working and that you are actually getting airflow. So when you start a cut, if the system is in this state, which is everything off, when you start the cut, you should look over to this screen and you should see that the roof exhaust fan turns on, and you should see that your laser cutter's blast gate is indicated as open. You should also look in front of you and make sure that this blast gate is in fact opening and that you are getting airflow and exhaust through the laser cutter. The next thing we need to do is place our workpiece into the laser cutter, and we need to set the focal distance for the laser. So we need to focus the material to the laser. And we do that with this little focus tool. This tool comes off, but we place it on and it balances on the side of the lens. And then our workpiece down here, we bring that vertically. So we start with it low and we bring it vertically up slowly using the controls on the laser until it just contacts this piece. Once it contacts this balancing piece ever so slightly, the piece will fall off. And we have a video of this happening to show you. So what we're doing now is bringing the material slowly closer and closer and closer, and it just touched, and now the material is in focus. So now that we have placed our material into the machine and we have verified that our cutting parameters are correct and we have focused the material to the laser, we now need to make sure the machine knows where to cut on the material. So we're going to use a combination of the directional controls and the red dot laser pointer in the machine to position the job where we want it to be cut. Now, this is a very low power laser. You don't have to worry about touching this laser or putting your hand under this laser pointer. It is just like a presentation laser pointer. When the machine is connected to the software job control, the location of this dot is represented by the crosshairs. So if we move this dot in any direction, the crosshairs on our screen should move. So by using these controls, we will be moving this dot around the workpiece, and that will in turn move the crosshairs around in our software. So here are 5 different options. If we were to place the crosshairs in the middle of our job, then the red laser pointer would be right here and the job would be cut around the laser cutter. If we were to put the crosshairs here, the job will be cut to the left and upper of our laser pointer. If we were to place the crosshairs here and our job here, the job will be cut to the lower right of our laser pointer. So decide which one is right for you, position the laser pointer where you'd like it to be on the workpiece, and then use your mouse to grab this file in job control and move it to the crosshairs. So now you are basically ready to go. You should note the settings on the parameters up here. These should be the default settings. Cut your job and try as best you can to evaluate if your job cut correctly without moving it. And if it didn't cut correctly, then you can start to experiment with other values of these parameters. There is a small icon. It looks like an eye. This is called the "What you see is what you get" icon. If you click that icon, instead of your job looking like a black box, it will look like the actual contents of that job. So that is a good thing to verify before you start. And then to start your cut, you press the play button down here. And again, once you hit play, the laser should jump to life. You should verify that the exhaust is operating, and you should watch the cut. And the big thing is you do not leave the area while the cut is in progress. While you're cutting, you may notice very small fires. These are normal. So if there is a small fire that follows the cut, so the laser beam is here, if that fire follows the laser beam and it extinguishes as the laser beam is moving, that is typically okay. However, if a small fire erupts and it does not go out, there should be small water bottles with spray nozzles near the laser. You can stop the job, open the lid, and try to spray to put those fires out. You should also verify that there is no smoke buildup in the build chamber. Smoke should be actively being exhausted from the chamber. If that's not happening, stop the cut immediately. And the biggest thing is, do not leave the laser cutter. You must stay with the laser cutter. Even if you have a 50-minute engraving job, you cannot walk away from the laser cutter. You must stay there. If you know the job is going to be long, bring your laptop, roll a table over next to the laser cutter and work right next to it. But we do not want to see you going to the bathroom, leaving the makerspace, or walking away from the laser while the laser is running. This is a big no-no. You may not walk away from the laser while your job is running. When you are done, it is your responsibility to clean up. You must leave the laser in the state that you found it, with no material in the laser, no scraps from the material you cut left on the tables around near the laser, and the laser should be clean. Also, if you have large pieces of material left over that you do not want, you can give them to the Makerspace staff and they can file them as free material for other users to use. And lastly, we'll see you guys back here after the last set of quiz questions. And that is it. We hope you guys enjoy using the CO2 laser cutters at the Makerspace, and we hope to see you around the space making wonderful things. Happy making!